Hey guys, Winston Mosley here. We're going to take a look at the thermal analysis setup for a winch system in lunar surface operation. Alright, so we're going to jump over to our model here. So this is a pretty simplified model. I don't have any fasteners. I don't have gear teeth on this worm gear. Obviously, it's simplified. And I'm actually going to simplify it even more by getting rid of this shaft and the gears and the spool here. They're just not necessary to understand what's going on with our steady-state thermal analysis. But we will want to save all of this stuff as a step file so we can import it into ANSYS. Alright, so if we jump over to ANSYS Workbench, when you first pull it up, it'll be completely blank, and then you can double-click here, Steady State Thermal, and pull in your, model. So that's this guy. If I click on Engineering Data, I can run in here. It'll auto-populate with structural steel, but most of these parts are aluminum, so you can run over here, General Materials, here's aluminum, and then you can add it to your workspace here, or whatever other material you need to use. So if we jump back here, then we want our geometry. Here, I've already imported this, otherwise it says import geometry, so now they want me to replace it. And then you can browse for it, or it recognizes that I've already uploaded this winch step file. Alright, and then we are going to jump over to our model. That'll pull up ANSYS Mechanical. So here's our geometry. You can see, it's what we just talked about. Here I've I've just suppressed these parts that I'm not interested in worrying about. But for everything else, it'll come in here. The material will just automatically be structural steel, so you'll have to set that to whatever you want it to be. You can just click on it, structural steel. Or jump back to aluminum. No problem. Run through all those. Materials, you'll see you can get more information about what they're actually using. And then aluminum's the one I pulled in. This connection is pretty important. I'm leaving most of these as program controlled. This thermal conductance is really what I'm interested in, except for this guy. So this guy, you can sort of tell here, it's the bottom face of this motor and the top face of this base plate. I don't want that to be program controlled because it's not going to be tightly connected here, and there'll be less thermal flow. So I've just set this to a much lower number, and that'll give me a reasonable value. I've already run some sensitivity analysis and determined that that's not hugely important, so I'll just leave it. Then we're going to run in here this mesh. Obviously, you can select a tighter mesh, but for thermal analysis, this is perfectly fine. The engineers I've worked with at Lockheed Martin, they would actually just run like the motor here as a single element, so this is overkill, honestly. Then we'll come in here, for the steady-state thermal. You can insert, your boundary conditions, your forcing functions, what have you. So I'm interested in a heat generation term for this motor here. I know this is 0.8 watts because I've already done some efficiency analysis on the motor that we were interested in. And then you can bump it up to see what it should be. Given this geometry, it wants it in a watts per meter cubed. So you just have to run through size it according to the geometry. If we take a look at this radiation term here, this radiation 1 and 2 are paired, if you will. They have the same enclosure number here and this surface-to-surface correlation. So the heat coming off of this face will reach this face, right? So the way that you set that up is with this surface-to-surface correlation and then the same enclosure number. I'm going to leave this as an enclosure type open. It's a little complicated, but basically if the other option is perfect, and if it's perfect, then all of the heat coming off of here hits this surface. That's not exactly what's happening, and ANSYS will throw an error if you try to run it like that. So instead, I just have this ambient temperature, so whenever it runs into an error, it just radiates to an ambient temperature of 120 C. That's higher than anything I expect to see, so it's not going to be an issue. It'll be conservative. So here I've selected the inside of this doghouse, and then with this radiation 1, it's all of these faces that I expect to radiate out to those other faces. Alright, and then with radiation 3 and 4, this is the top surface, and then this is the bottom surface. I can jump back to here. So this is radiating to the lunar surface at 121 C, and this guy is radiating to space at 4 Kelvin. Very cold. And then these heat fluxes here, these 3, are all incident solar radiation. So I've picked a specific vector, roughly like this. So this face is irradiated, as are these faces here. And then this face is also irradiated by the solar radiation that hits the moon here and then bounces up. That also hits these guys. So I've set all these numbers to correlate with whatever is applicable. These two here is something I kind of added later. That's all of these side faces. Both of these geometry selections are exactly the same, but they are radiating both to the lunar surface and space. I set the emissivity here just so that it would roughly correlate to 40% space radiation and 60% lunar surface radiation. Here for the solution, I'll just insert thermal temperature. That's what I'm interested in, and I've already done that. Alright, so we just went in here, solution, solve. It's not in here because I just ran it, and it'll take a minute. So it has a status bar down here. When it finishes, it'll say ready, and now we can take a look at the temperature information. Alright, so I've hidden the doghouse here just so you can see what's inside. The doghouse is not super interesting, but I do have an image of it in the report. So here we can see our motor is the hottest part. It's not quite ideal, but if you look at your temperature spread, it's only about 0.4 C. So it seems like this whole system is going to have to cool off somehow if we really want any particular part to be much colder. Specifically, we're interested in the motor. So now we have a predicted temperature. All right, well, so that means that whatever motor that we actually want to buy and put in here has to be reliable and work at well above this temperature. So we might say 140 or 150 C, depending on what your thermal margin should be.